Welcome to today's First Chesapeake Chat session. I'm Victoria Mulvihill, and I'm here to introduce the First Chesapeake Chats sponsored by Newport News Shipbuilding. I would like to thank this session sponsor, Dominion Energy, for making this chat possible. Just some housekeeping, we'll let the presenters speak and then open up for discussion questions later on if there is time. If you have any questions throughout the chat, please feel free to put them in the live comment section. The session today is Cool Jobs, discussion with first mentor Andy of the Johns Hopkins Applied Physics Laboratory. And I'll now pass it over to our speaker, Andy, to introduce himself.
Hi, Victoria. How are you?
Good. How are you?
I'm just, living the high life here and amongst my basement, like everybody else. Anyway, as you introduced me, my name's Andy Driesman. I work for the Johns Hopkins University Applied Physics Lab. We're one of the, when people think of Johns Hopkins, they mostly think of the hospital and the university. But we're a group of about 8,000 people located in Columbia, Maryland, or just south of Columbia, which is about halfway between DC and Baltimore. And I've been working there since 1997. I moved down from the Boston area and started working there, and I have no intention of ever leaving there. Because I have what's probably, I thought I had the best job in the world. So it's interesting that in the byline it said Parker Solar Pro Project Manager, and that's true. I was the Parker Solar Pro Project Manager through its development, and I will talk a little bit about that. But currently, I thought that was the best job in the world, but now I think I really have the best job in the world. I'm the spacecraft manager for a mission called Dragonfly, which is to fly a drone on the surface of Titan.
Oh, wow.
Yeah. So it's I'll start a little bit about Parker Solar Probe. Parker Solar Probe was so just let me back up a second. The Applied Physics Lab is one of 3 organizations in the country that produces complete missions for NASA. So NASA is the National Aeronautics and Space Agency, the U.S. Space Agency. And we do a lot of work for the Science Mission Director. So almost all our work is doing these large science missions for NASA. The lab has been doing that since the late 50s and has been very successful ever till today. Parker Solar Probe was a mission that was launched in 2018. And my work on it started in 2011. And that mission was designed to answer some fundamental questions that we didn't understand about the sun. In fact, the mission was originally conceived in 1958 and actually predates NASA. So for 60 years, the scientific community had some basic questions about the sun that they weren't able to understand. The 2 big ones are, if you think of the sun is a big hot ball of gas. And if you think about it, the closer you get to the sun, the hotter it should be. The further you get away from the sun, the cooler it could be. It's sort of like a fireplace. You get close to the fireplace, it's nice and toasty warm. You get back away from it and you start feeling the chill of the room. The sun is the exact opposite. The further you get away from the sun, the hotter it gets. So the surface of the sun is about 10,000 degrees Kelvin. As soon as you get further away, say, 20, 30, 40 million miles, the plasma temperatures are up in the millions of degrees. Really don't understand what causes that. The sun spits out the solar wind, which is this energetic particle stream that is produced by the sun 24 hours a day, 7 days a week. And it accelerates it from the surface of the sun to speeds that are able to escape the gravitational pull of the sun. Don't quite understand what causes that, the genesis of the solar wind. And in order to understand that and why it's been a question since the 50s, you actually have to go there to figure it out. So starting in the mid-2000s, NASA worked with APL to develop a mission that could actually go close to the sun. And that mission went through the development from mid-2000s and launched in 2018. And it gets, at closest approach, it'll be about 4 million miles off the surface of the sun. Now, 4 million miles seems like a lot, but that's actually, the Earth's about 100 million miles. So if you pictured yourself in a, so you next to another person 10 feet away, if you got to within 0.4 feet, that would be the equivalent of how close the probe gets to the sun. At the closest approach to the sun, the temperature is horrific. The spacecraft itself gets up to about 2,500 degrees Fahrenheit. There are 3 megawatts of energy on the front surface of that. Yet the system is cleverly designed and has a carbon-carbon heat shield that protects all the instrumentation. So I was manager of that mission, and I worked with teams of scientists and engineers from around the world to conceive, design, develop, fabricate, integrate, test, and eventually launch that mission in 2018. After that, I took a nice long break doing a bunch of other things. And as of the beginning of this year, I started working on a mission called Dragonfly, which has received quite a lot of press for NASA. And that's a mission that we're just starting now, and it actually launches in 2026, and it goes to Titan, which is a moon of Saturn. Titan is unique in the solar system in that it has, if you wanted to find a place that had complex hydrocarbons, so the Earth is full of complex hydrocarbons. We're made of complex hydrocarbons. If you wanted to look at a place that most similarly looked like Earth as it did millions and millions of years ago, you'd actually pick Titan. Titan is a moon of Saturn that has the second highest concentration of complex hydrocarbons in the solar system. And the goal of the mission is to go look for what we would call prebiotic life, biochemistries that could possibly lead to life. The interesting thing about Titan is Titan has a gravitational pull that's about 1/7 of the Earth's, and has an atmospheric density that's higher than the Earth, which means if you wanted to move around Titan, the best way to do is fly. So the process of developing a nuclear-powered octocopter that will launch in 2026 and fly for 8 years, doing numerous gravitational swing-bys, and arrive on Titan in 2034. And then it'll fly around Titan for a couple of years, sampling the surface, looking for complex hydrocarbons and trying to understand the chemistry of Titan. So I'm managing that. I'm managing the spacecraft, which includes the lander itself. It includes in order to get into the Titan atmosphere, it needs a heat shield. So managing the development of that heat shield, as well as all the analysis that goes along with that. And so that's my job now.
That's so cool.
It is pretty cool.
I mean, so, that's a cool job.
It's a very cool job. So yeah, I'd like to say that in Solar Probe it got very hot, and now we get to go to Titan where it gets very cold.
Yeah, that's really neat. How do you, like, you said you're product manager, like I'm part of these teams. So how do you prep for something like this? Like, what kind of analysis and stuff do you really look at when you're trying to figure out if something can survive in these extreme temperatures and collect the data that you want it to?
That's a very good question, and it's a very complicated answer. And it's, matter of fact, a huge amount of time and effort surrounds the ability to assure ourselves that whatever we launch there could actually operate in the Titan environment. The mission is total cost is probably about $1 billion, $1.5 billion. And with that investment, it better work.
Yeah.
And so we do a number of things. For things that we sort of purchase and use what would be considered off the shelf, you look at specifications. So like robotics, if you're going to use a motor, say from Andy Mark, and you want to know how much torque it produced, you would look at the torque curve that comes out of Andy Mark. We do the same thing with the equipment we purchase. the information we get is significantly more than what you get from anti-mark. It's essentially the same thing. And you look to see it'll survive in the environment. For things we develop, i.e. we build them from scratch, we need to do a bunch of analysis that will prove that it'll exist within the environment. So you worry about not only the cold temperatures, but you're worried about what would be called CTE, which is mismatches in temperatures, where you have something, say, that's hot on one side and cold on the other side. And so one side's going to want to expand and the other side's going to want to contract. And so you do analysis to assure that the thing doesn't break. But ultimately, analysis is only so good. And in the end, you end up testing. So one of the things we're doing at APL is we're building a chamber that can mimic the environment to Titan. So the Titan atmosphere is mostly nitrogen, but it has a fair amount of methane and hydrogen in it. And so we'll build a pressure chamber at APL that's able to mimic the environment there and also to get as cold as it can in Titan. And so we'll push instruments and components through that chamber to be able to assure ourselves that it'll actually work. In the end, you sort of have to glue all this together, and you have to prove to yourselves, you have to prove to NASA that you've looked at every single thing on the spacecraft, look at the environments it's going to go into. That includes the fly out. At Earth, it's relatively warm. It gets to Titan, it's getting colder. There's radiation environments to deal with. There's energetic particles from the sun. That's the solar wind I talked about earlier. It could be your friend, it could be your foe, and it can impact you. So we have to look at all these environments and assure ourselves that it'll work.
So obviously, with any engineering challenge, we see this in FIRST robotics and we see it in real world applications. There's always something, the talk of failure when you do something and it doesn't work, or you try one thing and it doesn't work, but that's how you learn from it. So what are some of like the biggest challenges that you've had to work with, and like what happened with it?
So what you say is absolutely true. We learn much more from our failures than we do from our successes. I would also argue that organizations are shaped by their failures. So if you look at NASA as an organization and want to really understand how NASA works, you have to understand Challenger and Columbia. So those were the two space shuttles that failed, and human life was lost. And those missions, which were in the 80s and the 90s when they failed, define NASA today. So the goal for these sorts of things is to, if you're going to fail on the ground and fail early, because the cost of failing after you launch is prohibitive. NASA will invest, in this case, more than $1 billion, and to have a failure after launch is considered unacceptable. With that said, NASA understands the risk associated with you. You can't design something that won't fail, and you can't prove to yourself that it won't fail. So there's always some inherent risk. So the objective of any test program that we develop, or any analysis program, is to get things to fail on the ground. And so we test things in succeeding levels of complexity. So if we were to build a structure, we would get parts of the structure and we would test those. And once those pass, we put them together into a bigger structure, test that, and so on. And the idea is to try to identify failure early. Like the robotics community, we have lots of failure. What I tell people when they plan their program, so you try to figure out how many people you need, how much it's going to cost, how much time it is, that they should plan around one failure on any given item. Don't plan for two. We're pretty good. Let's not have two failures, but let's have at least one. We've had failures. Solar Probe, the failures were interesting because when you try to mimic the temperatures associated with the sun, you're using a lot of high energies. So now it's interesting to go back and think about it, but we've had failures. We were testing a heliostat, which is a big series of mirrors. And what we were doing is it's basically like a big magnifying glass, only a reflector. And we were always focusing these mirrors on a chamber to test a solar array. And we were sitting there tuning the mirrors up, and we weren't paying attention that we were actually increasing the intensity of the beam until we looked around, and where the beam was focused was on this aluminum strut, and it had melted through the aluminum strut, and it was dripping aluminum on the ground.
Oh my goodness.
We've had, I wish I had saved them, a rogues gallery of all the fires and burnt and charred pieces that we had on Solar Pro, because the failures aren't so much of the hardware. Sometimes it's the failure of the test you're doing. So you plan on doing a test and planning on being able to mimic the environment. And it turns out the test yourself, the test environment becomes a failure unto itself. So lots of experience with tests, and you learn from them. And so you learn about all the things you shouldn't do.
Absolutely. And you mentioned that, when you are advising people within the FIRST community on stuff on the failures, what led you to FIRST in general?
Well, my kids. So I've got two boys. Both of them went through the FIRST program. My youngest went through FLL and FTC. My eldest went through other sort of STEM activities that ended up with FTC. And then they left the FIRST program, and my wife and I hung on for a few years. So I'm still part of the FIRST program by doing this. So FIRST is, it's got, so when I think about it and how it relates to the job I do, and one of the things I actively do is I do work with FIRST kids to find them, help them with internships, and try to, I'm a big believer in the program. If I see resumes and there's FIRST experience on one and not FIRST experience the other, I will lean towards the FIRST experience because I know how valuable it is. And the two reasons I say that, one is that when you build something, whether it's hardware or software, it's a lot different than being at school. School is, I'm going to state the obvious, is very academic. And you're doing a problem, you get the problem wrong, you get an X, you try again, you get the problem right. The cost of failure is very minimal. When you're building your robot and you're there at 8 o'clock and everything's, in the evening, everything's running fine, and you go, oh, I'm just going to run this one more time, one more test, see if I can score whatever I want to score, and then the thing stops working.
Yeah.
Because we've all, I'm sure every robot person has experienced that. That's life. That happens in the real world as well. The other thing I think that's valuable is first is you're forced to work in teams. And it's not only your own team that you have to worry about, it's the fact that you're in alliance selections. And my favorite part, I'm an FTCer, I'm not an FRCer, but so I'm assuming it's the same in FRC. My favorite part of any competition is alliance selection. Because that's what I call it the mating dance. Have the teams who are going out looking for other teams and trying to sell themselves. That ability to go out and sell yourself and sell your product, and the ability to convince somebody that you may not be the best on the street, but you have something that they need, is a skill that is invaluable in the real world. And that social interaction is not something you really get from, certainly there are very few sports you get that in. Matter of fact, I can't think of any offhand. And it's something that's very desperately in the world. We compete viciously with organizations. So Goddard Space Flight Center and APL compete constantly on things. Yet for Dragonfly, we're teamed together. We're building the drone, the lander, and they're providing a big instrument that measures the complex hydrocarbons. And we team together to win this program from NASA. So real life is sometimes you compete, sometimes you team. And the same person, you could be competing one day and you could be teaming with them the next. And that's direct experience out of the FIRST community is a big leg up for that sort of, for understanding that environment.
I think that's a great way of putting it. I mean, you have to have that experience in order to, and FIRST gives you that experience of working with people all the time and not always knowing exactly what you're getting into when you first have that partnership, but then learning from each other.
Yeah, if you compare it, to other activities, so you compare it to sports, you don't get that. If you compare it to your team projects in school, you don't typically get that. So FIRST is really unique in that aspect.
Okay, sorry, I was trying to read some of the comments, but I have a question for you, kind of based off of what you said about, school is a lot about teaching you things, but it's yes or no and, minimal failure risk. But I want to know specifically, like, what led you down this path to this job that, is your dream job, is the best job ever. And like, what kind of steps did you take through your education and to get to where you are?
I think that's a difficult question. I've been doing this for 30 years, so there's a lot of choices that I've made that landed me where I am. And I guess what I characterize it as willingness to take risk. So I have I have one non-traditional degree, right? So I have a degree in electrical engineering, but I also have a degree in geology. So not traditional for the job I'm in. I then went on and got a master's in technical management, which is maybe more traditional. But I think that when you think about careers or think about what you want to do, you're managing two things simultaneously. You're managing your capability. So capability comes with the things you do, the experience you get, but you're also trying to manage opportunity. And so you could be the most capable person in the world, but if you don't have the opportunity to express that, then you may be frustrated in your jobs. And I think the best way to deal with opportunity is to take appropriate risk. I'm an engineer, so I like plans. And so I had a career plan. My plan was to be the lead engineer on a significant NASA mission. And I did that. And so in 2006, we launched a mission for NASA called Stereo. And I was the lead engineer on that. So there I am in 2006, I'm 43, having finished my career goal. I had 20 years left in my career and I wasn't quite sure what to do. So I went and I ended up supervising a group of system engineers at APL. And that was a very good experience. And then I was looking for what to do next. And I had a choice. I could either just sit back and wait for something to appear or something within the lab. But it wasn't, as you try to predict the future, there wasn't much on the horizon. So I ended up actually working a year for NOAA, which is the National Oceanographic and Atmospheric Administration. They have the National Weather Service under them, which is you're probably most familiar with, as well as fisheries and things like that. And they handle the constellations of Earth weather satellites. And they needed someone to manage what's called their polar orbiting weather assets. It's a little complicated, very trying time for that particular program. They had spent a lot of money without much success. They had space fall on their sides. They had very dysfunctional relationships with NASA and dysfunctional relationships with Congress. And it was a position that there was really no way to be fully successful in. But more importantly, I looked at that and said, there's also no way it was so messed up that there was really no way for me to fail in that position. So I took a career risk and went off and did that. And in that process, I met a lot of key people who enabled my career in the future, because I was working at a level way above my pay grade. And so I met a lot of very influential people, and that really enabled a lot of the things I did in the future. And that's not so much the example as, that you should be looking for that, but it's the ability to take risk in your career and the ability to try something different, even if it's outside your comfort zone. So I would say that's probably the biggest thing in terms of enabling my career. And it certainly enabled me for doing Solar Probe. Those contacts were critical. And because Solar Probe was successful, Solar Probe was nearly impossible. I, was viewed as one of the few people who could actually do this on Dragonfly, which is also almost impossible.
Of course.
So I guess I'm a glutton.
You're willing to take that risk, which is really cool.
Yeah.
Can always lead to some cool things. I don't see any current questions, but we're low on time anyways. But if you have one last thing you want to say, some advice of a student or just somebody who's interested in what you do.
It's advice for the student. Enjoy first. Be passionate about it. It really does give you a unique outlook on life, and when you move on to college, you'll begin to see that, I think.
Well, thank you so much.
Sure.
And you gave us some great advice and just some really good input and just a great story. I mean, it's really cool what you were able to do and what your job is. So thank you for being here. And I'd also like to thank our sponsor for today, Dominion Energy, once again. We have a short video for you to watch, so please stick around and have a great rest of your day.